Okay, now we're going to go over the equivalence of resistors in parallel. So I'm actually going to draw something, I'm going to draw the same circuit twice. Okay, so you may have seen circuits like this. You may see something like this, where you have a resistor right here, and then you actually have another resistor right above that, something like this. This is the same as if I drew a circuit like this, and then I had two different paths to go. Again, beautiful artwork. I know. So again, so one resistor here, one resistor here, one resistor here, one resistor there. This is the same circuit. Although it doesn't look the same, it is the same. So let's look at this situation. Okay, before I have created an analogy where you drop something from a cliff. However, that was when there was only one direction, one way to go from beginning to the end. In this situation, there are two ways to go, and only two. No more, no less. You cannot do something interesting like go through here, pass, and then go do a loop and come back through here. You can only go in one direction. So you can, once you're at this what we call junction, you have two options, but you can only choose one. You either go this way or that way. And once you choose it, that's it. You finish that, and then you come here, and then you have to go to the bottom. Same thing here. You go, and you either go through this resistor, or you go through this resistor to reach this junction, and then you lose your potential energy, or you lose your electric potential. So that is one big thing. You cannot, again, I can't stress this enough, you can't go through this, come back, go up here. There's only, you're either going to go here or here. Those are your two options, whereas before you only had one, or technically zero, because there's only one route. But so now this is the part that's interesting. Before you only had one option, now you have two. So this is kind of unique. Before, instead of just dropping it, think of a water park again. You're at the top of the water park, of some slide, but you have two options. You can do this option or that option. It doesn't matter. So you choose one, you reach the bottom, and then you're here. Same thing here, okay? Let's think about that. Now, similar to the rock being dropped, once you choose that direction, you're at the top of the slide, and you have to reach the bottom. This is the part that's interesting. So let's call this R1 and R2, okay? I will have my value for the voltage right here will be 12 volts. And let's make R1 2 ohms, and let's make R2 3 ohms, okay? So remember, you have multiple options at the top of the slide to go down the slide. However, when you only had one direction though, let's only have one resistor. If this was 12 volts, hopefully you can understand the difference in potential between the beginning and the end of this resistor. So the potential drop through this resistor. If there's only one resistor, then the potential drop of this resistor is going to equal, so R1 would then lead to V1 equaling 12 volts. Because if there's only one, then the voltage here is going to equal to the voltage here. So before I show you the equation for the equivalent resistance of resistors in parallel, I want you to understand this, is that even though there's two options, and this might be a little tricky, the voltage for R1, let's call this V1, and the voltage for V2 is going to equal 12 volts, each one. Now you might be like, what? That doesn't make any sense, because, you know, that's 12 and that's 12. And if I add them up like I did in series, that would equal 24, which is bigger than here. So that's not possible. Au contraire, okay? Because you have multiple options, either option you choose has to drop the amount that if there are no resistors here, if it's just like this, one here and one here, it has to drop the amount that's necessary from the circuit. So because there's one resistor here and one resistor here, it's got to drop 12 volts from here to here, and it's got to drop 12 volts from here to here. Same thing from here to here and here to here. That's what you need to understand. And when we move forward with that, that's how we are able to figure everything out. Okay, so now that you hopefully understand that the voltage passing through here or dropping through this resistor would be equal to the voltage at the battery or the power supply, and then it would be the same for this resistor. So the voltage passing through here, 12 volts will equal to here. Now here's the thing that you need to understand that I haven't specified yet, is that remember in series current is the same. Now here voltage is the same, but let me tell you what's different here is that this current that is flowing through here will not be the same. Okay, think of this. If you have multiple ways to go in traffic, right, you and many people behind you, if you all went one way, that would get clogged up, so everyone will go the other way. Well, with electrons, they do that very quickly, but they will go to where it will flow, maybe not evenly, but through the path that seems a little easier, which means, okay, so let me explain what that means. It means that this current right here will be divided up, not evenly, but it will be split up between this path and that path. That's because there's only so many electrons that can flow through it from the beginning, that some of them will go here and some of them will go here, which means that the current coming from the battery is going to be different than the current going through each of the resistors. So this is going to get split up. This current is going to get split up, part of it through here and part of it through here. Let me draw that again. So again, it's the same circuit, but over here. So this current I is going to go split up here, and it's going to be split up here. So we can think of this as I1 and I2. So the current coming from the battery is going to be equal to the split right here. And then they're going to follow through, and then they will combine again, and this will be equal to I again. So the current coming in is equal to the current going out, and then vice versa. Does that make sense? So the current in series stays the same. So if I had multiple resistors right here, the current would be the same only through one loop. But if I have multiple loops, that current will be split among them, not evenly. Okay, so let me write that down right here. So the current I is going to equal to I1 plus I2. Because the current is one number, it's called conservation of charge. It gets split up between the routes. So let us figure this out, okay? Let me show you how we got the equation to the equivalent resistance. Okay, so current I is going to equal the resistance and the voltage here. So I'm going to change this into V over R1. And I'm not saying V1 because the voltage here is going to be 12. Do you see that? The voltage there is going to be 12. And then plus I2, the voltage is going to be the same. So I don't need to say V1 or V2 because it's the same. But for I2, it's going to be V over R2. 2. Do you see that? So I equals V times, if I take a V out, it'll be 1 over R1 plus 1 over R2. Now remember, I has to be V over the R. So what this means is that the equivalent resistance of these added together is equal to V over R. So if I have these equal to each other and I get R up here, the equivalent resistance, then I can cancel out the V's, bring this up here and bring this down here. My R equivalent is going to equal to 1 over R1 plus 1 over R2 to the -1 power. And that is how we get that equation. that is how we get that equation. And if I have multiple roots, if I have another one, then you just kind of keep it going. So let's do this. So the R equivalent here, R equivalent would equal to 1 over 2 plus 1 over 3. And remember there's ohms in there, because it's going to be resistance. So if I do this, then I need to find the common factor. So that would be 3 over 6 plus 2 over 6 to the negative 1. So if you do that, 5 over 6 would be 6 over 5. So my R equivalent would equal to 1.2 ohms. So notice that if they're different sizes, then it will be smaller even than the smaller one. That's kind of interesting. Let me do another one. Let me do another circuit very quickly. Okay, let us have this resistor be 10 ohms and then 10 ohms. Forget about that. Remember the equivalent resistance between these is going to be 1 over this plus R2 to negative 1. And if I had another one, then I would add that too. But if I have two and they're the exact same value, it's something interesting kind of happens. So R equivalent equals 1 over 10 plus 1 over 10. That equals to the negative 1. Don't forget that. That equals 2 over 10 to the negative 1. So if you do that, that would actually be 5. So R equivalent is 5, which is half of 10. So if you did that with 2 and 2, it would be 1. 4 and 4, it would be 2. And then any numbers that are identical, if they are in parallel and you do the equivalent resistance for them, it would be half of whatever the original value is. And then let me do another one with 3. 3, just to make sure that you really got this down. Okay, it doesn't matter what the voltage is. I know there's a huge difference there. That's okay. So let's do this. Let's just get some random number. 3 ohms, 2 ohms, and then 4 ohms. Okay, so my R equivalent will equal to 1 over R1 plus 1 over R2 plus 1 over R3 to the negative 1, of course. So then if you want, you can plug this into your calculator. Just make sure everything is, correct. 1 over 3 plus 1 over 2 plus 1 over 4 to the negative 1. I'm just going to do fractions because it's not too bad. It should be 12. So if you do this to 12, that would be 4 over 12 plus 6 over 12 plus 3 over 12 to the negative 1. If you add those all up, it would be 13 over 12 to the negative 1, the reciprocal, so that would be 12 over 13 ohms. Of course, when you do this, please give me the number, not the fraction. So that would be less than 1 ohm, which is funny because it's 3, 2, and 4 ohms, but if you add them all up, the total resistance would go down of the whole circuit. And that makes sense. Think about that. If I have multiple ways to go on the freeway, multiple freeways to take, in Arizona it's not that big, but in LA or really big cities, you can kind of see this multiple routes that you can take. If I had these together with one circuit that's in series, let's look at this. Boom, boom, boom. If I did this 3 ohms, 2 ohms, and then 4 ohms, you would have to add them all up. So this would be the R equivalent right here for this one. You just add them directly, that'd be 9 ohms. Compare this to that. The reason why this makes sense is because, look, if you had only one way to go and there were 3 different accidents, wouldn't your trip take even longer to go. But what if you were going one way, there's an accident, you saw it on your GPS, and you're like, you know what, let me go the other way, and then there's two other smaller accidents. If you had many cars behind you, you could all kind of just split up into these, and then the overall resistance wouldn't be that big a deal as if they were back to back to back to back. So that's kind of what that means. Hopefully this makes sense. If not, just send me a message. Peace out until the next video where I will combine those and those. Peace.